We're missing something. Oh, yes, maybe, what do you see him at lunch? No. He goes to all the places.
Into the server.
Okay. Maybe, let's see, maybe. Maybe you come out right very slowly. So let me summarize a summary of problems. Of main problems. So first of all, let's formulate it in a more general situation. So X now is a one-dimensional complex manifold. And let's recall what this should mean. It means the meaning of this is this, that there is a covering of X by open sets, and on these open sets you have diffeomorphisms. So this is a differentiable manifold onto open sets in the complex plane. So it's a differentiable manifold. So let's just say homeomorphism is the first. And then you have the usual change of coordinates. Just the usual notation. Let me repeat it for you. If we let u I j equal ui intersect uj, and we let phi of ui j equal vij. So you usually have this picture that everybody draws. Here's the manifold X, and here are the open sets ui and uj, this manifold, and here's the intersection. You want compatibility in the intersection. So you have phi here of the intersection, and so what you have here is phi inverse phi j. So you go up here from vi, here's the intersection here. You go back up here by phi inverse on that intersection, and you go back down by phi j, and you go over here. This is vij here, and had to have fun. This is called a vji. Right? Yeah. You change the coordinates. This is a vij to vji. Change the coordinates, and this should be biholomorphic. So in Professor Petra's course, in Cyril's course, this is just diffeomorphism. Right? That being a homeomorphism means that this is topological space and so on. You have open covering and so on. There's no, it's a joke. But to have a diffeomorphism by change of coordinates is already a smooth structure. And here we require biholomorphic. Biholomorphic. That means the notion of holomorphy is well defined. Right? So holomorphy in one coordinate system is the same as holomorphy in the other. So the notion of holomorphy is well defined, and we do complex manifold. We do complex analysis on these things.
Question?
Yeah.
So for multivariables, holomorphic would mean.
Yeah. Let me comment on that. He's asking in general what about more than one variable, and it's the same words, except that this is no longer so higher dimensions. And higher dimensions, okay, so x, say, is n-dimensional. This means that the coordinates phi, the same words, same letters, but you are landing with coordinate systems in Cn. And that was his question. That's not his question, he knows that, but the question is, you continue on about the compatibility, and the compatibility is then, well, this mapping here is usually called, I don't know, usually, I call this mapping Pij. Change of coordinates, Pij, is Pij is bihomomorphic, so Phi, Bi to Ji is bihomomorphic map of n variables. And now that's really your question, what does that mean? I assume that's what you meant by your question, and it's a good question, it's a very good question. Some of the people asked about it, I'm not sure who in the homework asked me this question and tried to answer it. So the definition first try is f equals f of z1 through zn. So that's his setting that I think I asked about, is n variables, holomorphic. So bihomorphic is going to be clear what that means, it's just a question what holomorphic means. Bihomorphic, if and only if f is holomorphic in each variable. That would be a first try of the definition, right? So let me use this is that I'll write down what that means. It's the Cauchy-Riemann equation. So this means the way I write the Cauchy-Riemann equations. It's just the partial derivative with respect to z of I equals 1 to n. And now, the first year analysis students would get very mad at this definition because it's very easy to have functions which are differentiable in each variable alone and which are not even continuous. Yeah. So you can really, this is a bad definition, you think. So the first attempt plus adding some epsilon in the definition, and for example, continuous. E.g. epsilon continuous. And then what you can do is you can prove the Cauchy integral theorem. This is enough to prove the multivariable Cauchy integral theorem. Multivariable, it's just one variable at a time, but the integral has to exist. A Cauchy integral formula. One variable at a time. You have the multiple integral and you just write one variable at a time. If you want me to do it, I can do it. So let's just f of zeta equals multiple integral of f of z over z minus z1 minus zeta 1, z2 minus zeta 2. So a multivariable variable Cauchy kernel, dz1, dz, a multiple variable Cauchy kernel. You just write it down one variable at a time, and you prove the theorem. But you see, if you're going to write this thing down, thanks. If you're going to write this thing down, this integral better exist. Now, for these guys in physics, they don't care. They say they're happy, and this is good to be happy. You just require this thing to exist, and you're finished. And continuity is certainly enough, right? Continuity is certainly enough. So, if you make this additional assumption, it's enough. And then came the great German mathematician named Friedrich Hartog, and who ended up in Munich. Hartog said epsilon is not necessary. And that is then a deep theorem. Okay? So, to answer your question, the first answer is, by anybody would answer, just one variable time, plus you got to make sure this Cauchy integral exists. Continuity, or maybe if you're thinking your real analysis in L2 or something like this, just make sure this or L, I don't know, it's just integrable. But in fact, you don't need much more. You don't need anything more. Okay? Fine. So that's the definition of a complex manifold in general. Hartog was a wonderful mathematician. And I think must have been a wonderful person. Okay, so one dimension, it's easy to, you don't have to answer Abig's question, it's holomorphic into one variable. Okay. And now the basic problems. Which now you can formulate anywhere. Problem one is the field of meromorphic functions on X. Meromorphy is defined in the same way. I mean, everything's the same. You have the local ring, you have the quotient. And you don't have a normal form, but you don't have our wonderful normal form. Well, you don't need it. The meromorphic function defined the same way and so on. Question mark, the quotient field of holomorphic. That's a very interesting thing. Meromorphic function is just locally pieced together. You have a global object that defines that. That's a really interesting question. Is every meromorphic function quotient to holomorphic functions? Problem two. This is the multiplicative problem that I talked about. You have the map, understand, maybe I'll formulate it generally, understand the map and from meromorphic functions, and now he was asking about this x, and I take out the zero function to the divisors of x. So in particular, this is called, I call this the map theorem. In particular, e.g., the naive question is every divisor, the divisor of a meromorphic function. That's an example of the image of this multiplicative homomorphism. And problem 3 is the same problem, but this is the problem I joked around it was going to be Alex problem. This is the problem, say, understand the map from meromorphic functions to, I call this H, to Hauptteile, Verteilungen, principal part distributions on X. So, for example, is every principal part distribution the principal part, let's call it principal part distribution of a meromorphic function. These are added, this is an additive morphism, this is multiplicative here. Now, I'd like to make several remarks about it. I think it's very important that you learn about these big problems. These problems are problems of construction. From my point of view. So, you give me a meromorphic function, okay, and I'm supposed to find two holomorphic functions so that the quotient of this two holomorphic functions is your meromorphic function. Right? That's really the problem number 1. Right? You give me a divisor. It depends how you want to think about a divisor, but poles and zeros prescribed in a good way. And I'm supposed to find a meromorphic function with exactly those poles and zeros in the multiplicative sense, or the same with the help. Do you understand? You really have to build something. You're standing there with X is standing there completely naked. X is standing there, you might like to see a naked manifold with nothing on it, no clothes. It's standing, just visualize a manifold with nothing on it. And you're supposed to construct these global things. Okay? Now, let us recall how you solve these problems in the case of differentiable manifolds. How do you build differentiable functions? I don't know if Professor Petra tells you this. I tell you this now. There's precisely one important tool. One and only one important tool. It is called partition of unity. It is called, yes? And this is how you do this. You piece together local things with partition of unity and get global things. You do it all the time. I'm sure you've already started to do it in Servan's course. And you use, and you saw it in the young people who were in my course. You saw it also in one dimension. I use partition of unity all the time. You need really partition of unity. Now, partition of unity is so non-holomorphic, it's not even funny. Right? Because it has compact support. I mean, it's zero in open set. Holomorphic function, nothing holomorphic is like that. There's no such thing as holomorphic. So the modern viewpoint to solving these problems is to solve them with partition of unity and say, oh, I can't do that. I get an answer, but it's with partition of unity. And you look at it, some guy says, you can't do that. You have partition of unity. That's not holomorphic. And you say to him, I didn't say it was holomorphic. It's something. Right? It's something. And then, but I'm going to correct it. So what I'm going to do is I'm going to correct it a little bit by adding something to it that kills off the problem of non-holomorphic. And in order to add to it, you need to solve a highly non-trivial partial differential equation. So from the analytic point of view, the subject of solving these problems is very close to solving some sort of partial differential equation. Now, that's the analytic point of view. Some of you are interested in algebraic geometry. So you might ask, what about the algebraic case? Now, what does it mean when you hear somebody say the algebraic case? It means the open sets are very big, and can be identified with algebraic submanifolds of some big Cn. Let me explain this to you. Let me explain this to you in dimension 1. Let me explain this to you in dimension 1. Okay. Here, everybody believes that's a differentiable manifold. This is a differentiable manifold of genus 3. And by the way, when you're making examples, you should always go to genus 3 at least, because genus 1 is genus 0, genus 1, and genus 2 are too special. Genus 3 is already pretty interesting. It's not special. So you have genus 3, and an open set here in the algebraic setting is the complement of finitely many points. So this is X, and U, the open set, maybe you have a point here. U is the X. It's very, very big in algebraic case. Maybe you have X2. Maybe you have I put here 5 points: X3, X4, X5. It doesn't matter how many points, but finitely many points. So the open sets in algebraic geometry, in complex geometry and algebraic case, so this is complex analysis in the algebraic case, the open sets are huge. They are the manifold minus a few points. Okay? And not only that, these things, these open sets U I are contained in some big Cn. So you have some big Cn, and these are contained there as curves, as this is UI embedded as a curve. But it's an algebraic curve. It's just a curve, an algebraic curve. It's wonderful. It's just a curve defined by algebraic equations. Algebraic geometry is taking algebraically defined things and pasting them together. Algebraically defined things are, for example, curves in Cn. Very interesting. Curve in Cn. Yes. And now you ask the question, what are the algebraic functions on the curves? Because we need to know. It's just like what are the holomorphic functions on the domain? What are the algebraic functions? On such a UI? Well, you don't have to lock yourself in a closet and think long. It's the polynomials. Yeah? So the algebraic functions are just polynomial restrictions of polynomial. So this is the algebraic version of complex geometry in dimension 1. You start with Petras Søren's for his lecture on calculus on manifolds, or Kavon's lecture last year. You have, for example, a compact case, but it doesn't matter. You start there. That's a differentiable manifold. Punkt, comma, aus. That's a differentiable manifold. Okay, fine. Okay, it's oriented. Good. We can integrate, no problem. Good. Now we consider, for example, compact case. Okay. What is it as a complex manifold? Well, you cover it. You want to have complex manifolds. So you cover it with open sets, which are identified with open sets in the complex plane. This is identified locally with complex analysis. Identified locally with, it's global if it's identified locally with complex analysis. Yes. And then somebody says, well, I can always do that. I say, yeah, Jack, but I'm going to require that the identification is compatible. Right? The change in coordinates is holomorphic. And you say, okay, great, you did that, then we have something really reasonably defined, and you have a complex analytic structure on this surface. And then, not in higher dimensions, but I'm sure Appig is also interested in this topic in algebraic case, because he likes to think algebraic. He says, what are you going to do in the algebraic case? What is going on in algebraic here? And actually, this is rather new that this was understood correctly in the algebraic case. It was understood by Zariski originally. He was Ukrainian. This is very, very popular nowadays to speak of Ukrainian. He moved to Italy and had the strong influence of the Italian geometers. But Zariski realized that you should use a certain form of algebra here, which I'm not going to describe right now, but he also realized what the open sets are. The open sets are not just open little neighborhoods like that. They're big. Complements of finitely many points in the case of a curve. And these open sets are identified with curves in Cn. Okay. And now what about the compatibility? Well, the compatibility means bi-algebraically equivalent, so I need to know what algebraic functions are. And algebraic functions are just restrictions of polynomials. That is the definition of an algebraic variety. That is not a modern definition, but it is more or less classical. Okay? That answers a little bit of a question.
What does it mean to have a restricted polynomials and restricted to some open set?
What?
What does it mean to have a restriction of a polynomial?
To the whole thing.
To the manifold.
So again, you start with, say, genus 3 Riemann surface.
Yeah.
An open set, coordinate chart, so to speak.
Okay.
Is I remove 5 points and I get a big open set. And I require in algebraic geometry that is equivalent, homomorphic if you like, to an algebraic curve in some big projective, in some big Cn. Okay, algebraic curve means defined by algebraic equations. I mean, that's all. Okay, and it's smooth. Okay. I get to that point, then you ask your question, what does it mean?
To be a restricted polynomial.
You take a polynomial, you restrict it.
To this.
To that curve.
Ah, okay.
You restrict it to that curve. Or maybe you take a rational function and you restrict it to that curve, but make sure it doesn't have any pulls on the curve. Something like this.
Okay.
It's algebraic objects on it. Just think algebraic. What's algebra? Algebra is polynomials. Yes? Holomorphy is power series. Complex analysis is the completion of algebraic geometry in that sense. Right? And that's the reason that complex analysis and algebraic geometry are very closely related. This is a special case of these algebraic things are very interesting. Now, I will not explain why, but in the algebraic case, so a fact, this is not fake news, it's a fact in the algebraic case, existence of many functions, in particular meromorphic functions, is free of charge. You don't have to pay anything in algebraic geometry. Quite often it is, you don't have to do much at all to get existence. Because after all, you have all of these polynomials on all these huge open sets. And you get many functions on your manifold. That is, in some sense, the reason why the first step in algebraic geometry is easy. Just the first step. Look at these problems here in complex analysis. Nothing is free of charge. You must construct all of these things. You must construct them all. Here they're somehow given to you by the big structure. Here you must construct these functions. Right? Deepak gives me a problem. He gives me a divisor. He says, I want to have a function which has a pole here of order 17 and a 0 here of order 45, and so on. He gives me this problem, and I'm supposed to construct a meromorphic function with that thing. Right? That's really non-trivial. Yeah? In algebraic geometry, it is also non-trivial, particularly later on. But you see, at least at first, you have a lot of free functions because of the coordinates. Okay? Yeah. Okay. That sort of answers some of the things that were underlying this discussion. Okay. Now let me just reiterate the history. Some words about the history. These problems were the guiding problems of problems 1, 2, and 3. Were guiding problems in dimension 1 for many years. And I would like to start with if X is compact. So let's look at this thing. Problem 1 and problem 2 for X compact. This was studied very deeply by the Berliner school. And in this Berliner school, plus Abel. So Abel, maybe you know the name Abel. You know the name because it's a very famous prize, which is called Abel Prize. It's a very nice prize for mathematics. And he was Norwegian, but he knew very well. He was in direct contact with the people in Berlin, and so out of the Berliner school. In particular with Abel together, and other such names here, such as Jacobi and Etienne and Weierstrass, and his student, plus his student. For example, the Douglas. And in some sense, we have a certain satisfactory answer given by Abel, which maybe if I have time at the end, I will write the answer. It is so beautiful. Every time I write it, I become happy. And that's Berlin X compact. X non-compact X non-compact, this is, I was talking to Prof about this in the break. X non-compact, there are many contributions of many people, e.g. For X equal the complex plane, then Weierstrass himself, and the entire Berliner school was involved in very important discussions of how to create solutions to problem 1 and 2. And then many other results, and finally, fundamental result of Benke and Stein. Since you're tired, I tell you stories to make you happy. Stein was a very good friend of mine. I had immense respect for him. He was a student of Heinrich Benke in Münster. Stein was drafted into the German army in the war. And he was sent to the Russian front, which was very dangerous because you could be killed very easily at the Russian front. And Benke was very close to the bosses in this matter, and convinced the bosses that Stein was a genius of coding. You know what I mean by coding. And so Stein didn't know anything about coding, but Benke convinced the boss that he knew something about coding. So they brought Stein back to Berlin, where he spent the war pretending he knew something about coding. And he learned something, and I think he did something, but he was saved. But they proved this theorem, Benke-Stein, in the non-compact case, for the general non-compact case, where the answer is yes to every question here. So also for problem 3. Very interesting. And now you ask about higher dimensions. This was the guiding problem in higher dimensions when the answer is yes. Because it is almost never yes. And you would be interested to know that differential geometric curvature plays a big role in when the answer is yes and when it's no. Curvature starts playing a big role in higher dimensions. In one dimension, you do not see any curvature consideration. But here, in higher dimensions, it became a guiding problem in higher dimensions. So Benke and Stein solved this problem, and what I will explain to you is Malgrange's PDE answer to this problem, which is much more general and much more insightful. You understand much more. So these are the guiding problems. Oh, I haven't mentioned for X compact. That's yes. Problem 1 and 2, and problem 3. For all problems, we've already solved for problem 3. For X compact, this is effectively Riemann-Roch theorem. Nobody knows who Roch was, but everybody knows who Riemann was. And Riemann, this was the guiding theorem for Riemann, is problem, in some sense, problem 3. Also problem 1 and 2, but problem 3. So this is the work of Riemann. And this is a guiding principle, a guiding question of this kind of theorem in geometry in general. To give you a feeling about the modern developments of this theorem, this was we started to discuss, so this is for a dimension of X equal 1, so Riemann-Roch theorem, and then later on, dimension of X equal 2. So when I write this, I mean complex dimension of x equal 2. We were asking about all these things we were asked about, and so on. This was the next thing. And there are two things here that you should know. This was the interesting context in Italian algebraic geometry. And the Italians didn't have any language to deal with this. They only had their genius to deal with this. So everything they said was probably true, but was not proved completely. Just proved by some sort of heuristic argument. So this Italian geometry was extremely important. You know, this is one big part of my own background that I'm feel very close to this period of Italian geometry. And to Max Noether. And Max Noether more or less solved this problem in algebraic geometry in dimension 2. So it is this problem 3. You can think it's a concrete problem. When is this mapping subjective? What's going on with this mapping from meromorphic functions to optiles? This is, in our modern language, a certain cohomological question. And Max Noether solved this problem in Erlangen. In 1900 plus epsilon, I think. And had big influence on the development of mathematics. And then, just to give you a feeling, I want you to get a feeling for what's going on here. That was the status of the situation in 1948. So this was the status of the situation in 1948. Yeah? Very interesting status of the situation of 1948. And this guy, Heinrich Behnke and his student Karl Stein were interested in this problem much earlier. And they solved this problem much earlier in 1941. But it's interesting that their result was published in 1948. You can guess why. There was the war between. And the first part, Stein was in some place near Leningrad. And then he came back to Berlin and had to do coding, and so they couldn't write up the paper until 1948. But the paper is fundamentally true. And in 1948, at the end of the war, well, at the end of the war, as you know, some of you people maybe don't know because you come from other places, but the war ended in 1945. I suppose you know all of that. Yes, yes. And the war ended in Western Europe here. I don't know. Yeah, you're from Kyrgyzstan, right? So, was the German army in Kyrgyzstan? Do you know?
No.
No. So you were saved from all of this.
Yeah.
Well, that's good. But Stein was not saved from this. Yeah. And in 1945, there was a very interesting thing. After the war, there were prison camps here in Germany. 1940 is a very interesting date. That's the beginning of Germany, right? Germany, isn't this?
49, I think.
49? When was the Währung?
Did you do that?
When did money start existing? It's an important date.
Yeah.
Maybe 48. It doesn't matter. There were still people in prison. In American prisons here. German soldiers were captured and were in American prison. Yeah. And I'm trying, you're very tired now, so I'm trying to amuse you with stories. So I will draw a picture that's very interesting. You see, this is the Rhine River. Yeah? And here is Bonn. Yeah. And here was a guy who saved himself somehow or another, and he lived over here on the hills on the other side of the Rhine. And he, after the war, he became the Chancellor of Germany. This man's name was Adenauer. He lived over here in Königswinter. Yes, and he was saved from all this war action, and he became Chancellor over here in Bonn. It's very interesting. I live here. So, AH lives right here. Yes, exactly on the Rhine. It's very beautiful. So I like this, and I like to think about this history. Yes, and here is a town called Bremen. It's a famous town because it had an important bridge, which the Americans wanted to use to cross the Rhine in the war, and there are big stories about it. It doesn't matter. This bridge is now exploded. It's gone. Yes, and the Americans had a prison camp here, were German prisoners. Not too bad the conditions. Yes, and in this prison camp, there was an 18-year-old soldier who had been drafted into the German army. He didn't have anything to do with it. He had to draft. They came and got him, and he had to go into the army. And he was in prison camp. And the name of this 18-year-old soldier is Friedrich Hitzelsberg. And Friedrich Hitzelsberg was in. I know where this is. I go walking here, and I think about Hitzelsberg. He was 18 years old in prison camp there, but only for a half of a year or something, very soon. And he left the prison camp officially, and he came and he lived in a small town near Münster, where Stein grew up. Where this Stein grew up. This town is called Hamm. It's called Hamm in Westfalen. There are many Hamms, but this is Hamm in Westfalen. So there's a Hamm. Stein grew up, and Hitzelsberg's father was a teacher in a school, and knew Stein as a result. And Hitzelsberg went to Hamm, and he met Stein at age 18, and Stein said, "Come with me to Münster. Come with me to Münster, where Weierstrass had done his work, where Heinrich Benke was the only professor in Münster at the time, the only professor, and studied with Heinrich Benke." Hitzelsberg went to Münster and studied with Heinrich Benke starting about in 1948. And in 1953, 5 years later, he proved Hitzelsberg Riemann-Roch theorem. That means that he solved as best as possible everything here in the algebraic case. In the algebraic case, which is much easier. But still, this is very fantastic, right? So we owe a great deal to Hitzelsberg. Hitzelsberg also built up Max Planck Institutes in mathematics in Germany. This was a trivial thing, by the way, you should know, this is trivial for physicists in Germany to build up Max Planck. We have experimental physics, we have atomic reactors and all this, and we have big money and all this, yes. But for mathematicians, it's very difficult. So what Hitzelsberg did, there are 2 Max Planck institutes, and it's really Hitzelsberg's, we say Hitzelsberg's Verdienst. It's his merit that this has been done. But what big merit was, that was his Habilitationsarbeit 5 years after prison camp. Yes, really, really, absolutely incredible what he'd done. And this is, nothing happened after that until the analytic case. And the problem is finally solved, solved at least theoretically by Attila Singer in next year. So that's a huge story starting with Riemann. It's really the goal of understanding these 3 problems in algebraic geometry or in complex analysis. With problems in algebraic geometry, it's easier because you have so many algebraic functions available. Okay, let's start. Okay.